Background. In the first part, we'll talk about what a greedy algorithm is. Greedy algorithms are the problem-solving techniques that build a solution piece by piece, always choosing the option that looks the best at the moment. They are useful for optimization problems like coin change or task scheduling, where taking the best immediate choice leads to a globally optimal solution. This method is simple yet powerful, and it works well when the problem was that called the greedy choice property. Greedy algorithm overview. The key principle behind greedy algorithm is making the locally optimal choice at each step. This only works if the problem also has optimal substructure, meaning that the problem solution contains solution to problems. That's why before using a greedy method, it's important to make sure the problem fits these properties. Thank you!
Time complexity. Big O notation. The time complexity of a greedy algorithm depends on the problem. For example, the coin change problem, solved greedily, can have a linear time complexity of 0n, where n is the number of denominations. In more complex problems, like Huffman coding, the time complexity increases to 0n log n, usually due to the use of priority queues. Big O notation. How code slows as the data grows. Number 1. Describe the performance of an algorithm as the amount of data increases. Number 2. Machine independent. Number 3. Ignore smaller operations like 0n plus 1 to 0n. Examples: 0, 1, 0n, 0 log n, 0n squared. N is representing the amount of data, or it's a variable like x. Here's the graph to represent the difference run of time complexity. We have data represented by data will increase as go more to the right. And we have the time. This is the number of steps. Let's start with 0, 1. Constant time. Random access of an element in an array. Inserting at the beginning of the linked list. Number 2. 0 log n. Logarithmic time. Binary search. Number 3. 0n. Linear time. Looping through elements and array. Searching through a linked list. Number 4. 0n log n. Quasi-linear time. Quick sort. Merge sort. Heap sort. Number 5. 0n squared. Quadratic time. Insertion sort. Selection sort. Bubble sort. And number 6. 0n 1. Factorial time. Traveling salesman problem. What makes greedy algorithms efficient is that they don't have to explore all possibilities. They often rely on sorting or simple selections, which makes them scalable and faster on large datasets. However, we have to study the problem carefully to see if a greedy approach will actually give us the correct result. Thank you.
Real-life simulations. To simulate the greedy algorithm, we used the coin change problem. The goal was to find the minimum number of coins needed to make a specific amount using a set of coin denominations. This problem is relevant to real-world situations like how ATMs dispense money or how vending machines gauge change. So tested cases. This is we tested both standard and tricky sets of coins. For example, we use US denomination like $1, $5, or $10 and $25, where the greedy algorithm works perfectly But we also tested where artificial sets like 1C, 3C, and 4C, where greedy doesn't always give the best solutions. The results and observations. In most cases, greedy perform well, especially when using common coin sets. But in some test cases, it didn't find the minimum number of coins, which shows the algorithm's limitations when the greedy choice property is not satisfied.
Performance evaluation. We evaluated the algorithm based on how fast it ran and how good its solutions were. Greedy was fast in every test case, but the quality of the solutions varied depending on the coin set. Method of evaluation. We compared the greedy solution to one generated by dynamic programming. Dynamic programming always finds the best results, but it takes more time and uses more memory. So, we look at the trade-off between speed and accuracy. Findings. The results showed that greedy works great when the conditions are right, but for problems where optimal solutions are critical and the greedy choice property doesn't hold, dynamic programming or other methods should be used.
And the last part is discussions. We have strength, limitations, and comparative analysis. First is strength. Greedy algorithms are simple, efficient, and often very effective. They are easy to implement and perform really well on problems that fit their structure. Second is limitations. However, they don't always give the best solution. Their success depends on the problem having the right properties like greedy choice and optimal substructure. Without this, greedy algorithms may fail. Third is comparative analysis. In terms of performance, greedy is faster than most other algorithms. But if accuracy is critical, we recommend using dynamic programming or other exact algorithms, even though they might be slower. That concludes our presentations on the grid.